So this energy escape art thing is pretty cool. We can take a look at the law of conservation of energy over here, and the the total energy here doesn't change. And so that's the law of conservation of energy. Really, energy can either be created or destroyed, but it can change forms. So where do I go here? Put another back down here, and so it can change forms, and it's going between kinetic and potential, pretty much. Kinetic and potential, kinetic and potential, and so a lot of times people can get the idea when it's going from top to bottom, because all the energy goes from height to velocity, from top to bottom, where it goes from height to velocity. But then you got to remember that we can go from velocity to height as well. So now the atom has velocity, and you can ask the questions in two ways. You can really answer it like this. Here I have potential energy from this being this height. How fast will I go? And so you let it go. Oh, that's how fast I will go. But you can also ask the same question backwards. You can say, okay, if I stop right there, now I have mainly kinetic energy. And you can ask the question. You can start it here, and you can say, hey, if I'm going this fast, how high will I go? And so here we go. This is how high I will go. And those two things are related through time, obviously. So on the test, there's a couple different ways to ask it. So first of all, you always want to know how much energy you have at the height, and it's pretty much all potential energy, and it's due to mass times gravity times height. And that will give you a number. If we call it 100 to make it easy, then if I let it go, then at the bottom, which I can't actually capture it exactly at the bottom, but the bottom, it's all kinetic and no potential. And so it's 100% would be kinetic. And so top and bottom is a very common thing to do in the world of physics, the question to ask. But then we're going to make it a little harder and say, what about right there? Or what about right there, where it's not exactly half, right? So then we have to employ the graphs and the height and the equations, where GPE equals mgh, kinetic energy equals 1/2 mv squared, and yet the law of conservation of energy is still true, that the total energy is still the same. Continuing on, then finally, we ask the question of how can we slow it down? And so when you're going a certain speed, it just flipped over. When you're going a certain speed, right? And if we can restart the skater, I'm going to throw away the thermal energy, and I'm going to restart the skater. If you can restart the skater, that speed and the height, there's not a lot of thermal energy lost. There's not a lot of friction. So it's just direct. But what if I add some friction? If I add some friction, then it will begin to slow down. And as it slows down, you'll see the third thing happening. And so once again, I still have this remaining the same. But now, instead of having just two items, I have three items to consider. And the slower it gets, the more the thermal energy you have. And so the energy doesn't go away. Like this item, this person can't fall because they're still in the middle of the path, but they've come to a stop. So where did the energy go? Law of conservation of energy says energy can either be created or destroyed. It just changes forms. And so in this case, it changes the friction, causes thermal energy, and the thermal energy is largely unusable in this case. And so there you have it. The law of conservation of energy with energy pie charts and with bar graphs.